Welcome to GATE class. So today we will solve some problems related to LTI system. I am Ravi Shankar from MITS Madanapalle. So the question is the system shown in figure 1 that is formed by connecting two systems in cascade. The impulse response of the systems are given by so impulse response of the system is given by H1t and H2t respectively, and H1t is equals to e raised to the power minus t into ut, and H2t is equals to 2 e raised to the power minus t into 2 e raised to the power minus t into ut. So this is our impulse response that is given. So according to this question, we have two systems. This is system 1 with impulse response H1t, and there is another system of impulse response H2t. These two systems are connected. This is our xt and this is our yt. So we have this so the impulse response, this H1t, so this H1t and H2t are basically they are in cascade. So let us do this problem. So what is the question? The first question is find out the impulse response HT of the overall system shown in figure 1. Okay, so what is figure 1? So basically we have to name this figure. So this is figure 1. So this is figure 1. Next is okay, so next part is determine the overall system, determine if the overall system is BIBO stable or not. So next part is, that is part B. Part B is determine is the system is BIBO stable or not. So this is our second part. So let us solve this problem. So I am again repeating the problem. So the system is shown in figure. This is our system. So this is our input, that is xt. This is our output yt, and we have two impulse response. First one is h1t, that is e raised to the power minus 2t into ut. Second impulse response, that is h2t, it is 2 e raised to the power minus t into ut. Sorry, I forget that. Now we need to find out. So what we need to find out? We need to find out the impulse response of the overall system, and second is we need to find out the BIBO stability. The second thing is we need to find out the BIBO stability of the system. Okay, so let us do that problem. So the first part is let WT be the output. Let WT be the output of the first system. So basically I am drawing again the system. So this is our xt, then this is our h1t, and this is h2t, and this is yt. So let this is W1T, let this is so this is WT, let this is WT. So basically this WT is basically the output of first system. So what is first system? If you draw this, then this is your first system. You are applying input to this system with impulse response h1t, and you are getting the output wt. So according to that rule, according to convolution rule, you have wt that is equals to xt convolution with ht, or ht convolution with xt, both are same. So what we are going to do, we are going to find out that we have the output that is so we have this wt. So wt is basically xt convolution with h1t. This is our first. So we have this again I am showing you that system. So this is our this is h1t, this is our x3 that is input, this is h1t that is impulse response of the first system, this is our first system, and this is wt that is output, and we are getting the output at this point at this terminal. So this is wt that is xt convolution with h1t. Now what is yt? Please see the system. Again I am drawing this system. This is xt, this is h1t, this is wt at this point. Now this wt is nothing but the input of this second system. This wt is nothing but the input of this second system. So we have, finally we have yt. So what is yt? So yt is nothing but wt convolution with h2t. Why it is happening? Because wt please erase this. Okay, so this wt is input to the second system. This wt is basically the input to the second system. So this is system 1, this is system 1, and this is system 2. This is system 2. So what is wt? Wt is basically xt convolution with, now this is equation number 2. So this is equation number 2. So using 1 into 2, we get wt is equals to xt convolution with h1t. Wt is xt convolution with h1t. So this wt we are using in this. So what is yt? So yt is equals to xt, since this wt is equals to xt convolution with st, so h1t, so yt is basically xt convolution with h1t. Let us take this bracket, and then after this convolution with h2t. So basically we have used one expression one, we have used we have substituted the value of wt in equation number 2. So this is our yt. So what is the finally we are getting? So yt is equals to so we can apply the commutative property. So we can apply the commutative property. So we can apply the commutative property, and this yt is written as xt convolution with h1t convolution with h2t. So if we analyze this, then we can find out that this is xt convolution with ht. Why? Because this is our input and this is our output. Now this is h1t and this is h2t. So basically if you put a black box here, then what is ht? So ht is nothing but h1t convolution with h2t. So this ht is basically the overall impulse response of the system. So ht is basically the overall impulse response of the system. This ht is basically the overall impulse response of the system. So thus we get with the given values of h1t and h2t, we have ht is equals to minus infinity to plus infinity h1 tau h2t minus tau d tau, because ht is convolution with h1t and h2t. So what is h1 tau? So what is ht? So what is h1t? So h1t is nothing but e raised to the power minus 2t into ut, and what is h2t? It is equals to 2 e raised to the power minus t into ut. Now just we are changing that scale. So right now we are just taking tau instead of t. So we have, what is h1 tau? It is e raised to the power minus 2 tau u tau. And what is h2 t minus tau? It is 2 e raised to the power minus t minus tau u t minus tau d tau. Now this is our this is our tau scale. So here we basically have tau equals to minus infinity to tau equals to plus infinity. So we can put that t terms outside this integration. So basically we have 2 e raised to the power minus t, we can put outside this integration, and it is minus infinity to plus infinity. The remaining terms are e raised to the power minus tau u tau u t minus tau d tau. Now please understand that, so let us discuss this equation. So what we are getting? We are getting ht is equals to 2 e raised to the power minus t minus infinity 2 plus infinity e raised to the power minus tau u tau ut minus tau d tau. Okay, so basically we can apply that the property of unit impulse here. We can apply the property of unit impulse here. So what is u tau graph? So if we see the u tau graph, so for tau greater than 0 for positive value of tau, u tau is equals to 1. So u tau is equals to 1 for tau greater than or equal to 0. It is 0 for tau less than 0. Now what is ut minus tau graph? So first you draw the u minus tau graph. So u minus tau graph should be like this. Basically if you time reverse this, so if we time reverse u tau, then we can get u minus tau. So what is u minus tau? It is nothing but just a mirror image from the horizon, and that reference axis is y axis. So basically it is time reversal of u tau. Now ut minus tau, so basically ut minus tau is if t is greater than 0, that is positive shift we are taking. Okay, so ut minus tau graph should like this. It should be like this. So it is ut minus tau. This is your t minus tau graph for t greater than 0, and for t less than 0 it should be like this. It is for t less than 0. Now for the sake of simplicity, because it is an impulse response of the LTI system, so for the sake of simplicity we are considering this scenario, that is t greater than 0. So this is our ut minus tau. So basically ut minus tau is 1 for tau less than t. So let us write this. So ut minus tau is equals to 1 for tau less than t, and it is equals to 0 for tau greater than t. Okay, so because this is our graph, and in negative also if we see that, so this is when t less than 0, this is when t greater than 0. So just analyze this graph. When tau is less than t, so just analyze this graph. We are considering this graph. So when tau is less than t, then obviously that u tau t minus tau is 1. So this is 1. In this graph also, when tau is less than t, we consider the negative case also, no problem, we will get the same result. So when tau is less than, here when tau is less than t, will go tau less than t is in negative axis, more negative value of t. Okay, tau. So basically suppose this is t equals to -1, then the tau is -2 -3 is obviously it is less than t. Suppose this is t equals to -1 for example, then tau is obviously less than t. So for both cases we can see that that ut minus tau is 1 when tau is less than t, and it is equals to 0 when tau is greater than t. So finally if we find out the product of that, so what is ht? We have written that ht is 2 e raised to the power minus t minus infinity to plus infinity e raised to the power minus tau ut minus tau d tau. So let us see this term. So the ut minus tau is obviously equals to 1 when it is equals to 1 when we have it is equals to 1 when we have two conditions. We have to make two conditions. First, this is u tau, this is u tau, and this is ut minus tau. So if we consider this case, then what is the overlapping region? What is the overlapping region? It is equals to 1 when we have, what is the overlapping region? So when we have 0 is less than tau less than t, and it is equals to 0 otherwise. So basically that integration limit, it will not go from minus infinity to plus infinity, it will go from 0 to t only. It will go from 0 to t only. So we have ht, so ht is equals to 2 e raised to the power minus t minus e raised to the power minus 2t into ut. Obviously because we are getting that positive, we are getting everything on positive axis only, because if we multiply this u tau with ut minus tau, then obviously there is no overlapping region, so ultimately we will get the product equals to 0. That's why we have taken from that tau range, we have taken from 0 to t only. Please let me explain this again. Okay, let me explain this again. This is very important concept. So basically you have this, you have u tau, so this is u tau, then second thing is ut minus tau for t greater than 0. So this is ut minus tau for t greater than 0, and this is ut minus tau for t less than 0. Now if we find out the product of these two terms, if we find out the product of these two terms, if we find out the product of u tau multiplied by ut minus tau for t less than 0, then obviously the product is equals to 0, because they are not overlapping, because they are not overlapping, we have u tau ut minus tau is equals to 0. Okay, and now if consider these two cases, then if we multiply these two graphs, then we can see that u tau and ut minus tau do overlap for t greater than 0. Now what is the overlapping region? So the overlapping region is this region. This region is our overlapping region. So from tau equals to 0 to tau equals to t, overlapping is there. Overlapping is there. So finally we can write this impulse response. So the impulse response ht is basically 2 e raised to the power minus t 0 to t e raised to the power minus tau d tau, because u tau and ut minus tau is equals to 1 for 0 is less than tau less than t. So after solving this, we are getting 2 e raised to the power minus t e raised to the power minus 2t into ut. So this is ht, that is overall impulse response of the system. Let us solve the problem, that B part, that's second part of the problem. Let us solve the second part. So the second part we need to find out the stability of the system. So what is ht? So ht is basically, ht we have derived in our previous page, we have derived the value of ht. So ht is equals to, okay, it is opening. Okay, so So ht is equals to 2 e raised to the power minus t into minus e raised to the power 2t into ut. This is our ht. Now we need to find out the stability of the system. So using the value of ht, we have, so what we have minus infinity to plus infinity modulus of h tau d tau. First we need to find out this minus infinity to plus infinity modulus of h tau d tau, because if the LTI system is BI-BO is stable, then from minus infinity to plus infinity modulus of h tau d tau should be less than infinity. It should be bounded. The impulse response should be integrable. It should be bounded. So we are going to calculate this value. So it is minus infinity to plus infinity. What is that ht? Using this ht value in this integral, we have 2 e raised to the power minus tau minus e raised to the power minus 2 tau u tau. This is modulus d tau. So what is the result of this integral? So it is 2 0 to infinity e raised to the power minus tau d tau minus 0 to infinity e raised to the power minus 2 tau d tau. Basically we have this we have written it from 2 to 2 times. Basically it is from minus infinity to plus infinity, so it is better to write in this form. This is same form. These two equations are same. Now what we will get, 2 1 minus 1 by 2. The solution of this is 1 and the solution of this is 1 by 2. Please check. So we will get 1 by we are getting 1 by 4, that is less than infinity. Basically so what is the conclusion is that that modulus of h tau d tau is bounded. So what we are getting is that impulse response is bounded, because the minus infinity to plus infinity modulus of h tau d tau is equals to 1 by 4. That is obviously it is a bounded value. So as it is satisfying the BI-BO criteria, so the impulse response is absolutely integrable. Hence we can say that the system is bounded input, bounded output stable. Hence we can say that the system is bounded input, bounded output stable. Okay, let us do another problem. So the question is, consider a continuous time LTI system. Consider a continuous time LTI system with the input output relation, given by yt is equals to minus infinity to t e raised to the power minus t minus tau x tau d tau. So the question is, first part, find the impulse response, ht of the system, What is part B? Show that the complex exponential function e raised to the power st is a eigenfunction of the system. Then in third part, find the eigenvalue of the system corresponding to e raised to the power st by using the impulse response obtained in part A. Okay, so this is our question. So let us solve this problem. So the problem is we have a continuous time LTI system. So this is our LTI system. The input is xt, the impulse response is st, and the output is yt. So what is yt? Yt is equals to minus infinity to plus infinity x tau h t minus tau d tau, and this yt is given in the paper. This yt is given in the question itself. So it is given as yt is equals to minus infinity to t e raised to the power minus t minus tau x tau d tau. So basically we have this. Basically this is our system representation for LTI system. So now we need to find out the impulse response. So what is impulse response? So basically when we are providing xt, that input is del t, that is impulse function, so the response we are getting is called the impulse response. So this yt is nothing but ht, and it is called the impulse response of the system. It is called the impulse response of the LTI system. So we have so what we are doing here, we have this xt, that is del t, and this is LTI system. So the output we are getting yt is nothing but ht, that is impulse response of the system. So ht is equals to, so according to the question, ht is equals to minus infinity to t e raised to the power minus t minus tau del tau d tau. Now we can apply that property. Of this delta function. So what is the property? If we have a continuous time signal gt multiplied with del t minus t naught, then it is gt naught multiplied by del t minus t naught. So what is gt here? Gt is nothing but e raised to the power minus t minus tau. And what is this del t minus t naught? It is nothing but del tau. So basically this is tau axis. Okay, so what we will get? From minus when we will solve this, we will get basically from minus infinity to t, just put tau, just put that the delay is 0 here. So we can get what we will get here. We have to put t equals to 0 in this So what we will get finally after this solving this integral, we will get e raised to the power minus t minus tau, and putting tau equals to 0, and this is for t greater than 0. So finally we are getting e raised to the power minus t into ut. So this is our impulse response, that is ht is equals to e raised to the power minus t into ut. So the impulse response of the system is e raised to the power minus t into ut. This is impulse response of the system. So this is impulse response. This is impulse response of the system. Now we have another part. The second part is show that the complex exponential function e raised to the power st is an eigenfunction of the system. So basically if you remember that the eigenfunctions, then this lambda, that is eigenvalue, is nothing but hs, that is transfer function of the system. So let us solve this part. So we have let xt, assume that let xt is e raised to the power st. Then what is yt? So yt is nothing but minus infinity to t e raised to the power minus t minus tau e raised to the power s tau d tau. So let us solve this integral. So t is independent of tau, so it is e raised to the power minus t. We can put outside this. So minus infinity to t e raised to the power s plus 1 into tau d tau. This is yt. So finally we are getting 1 divided by s plus 1 multiplied by e raised to the power st. So it is nothing but e raised to the power st if real part of s greater than minus 1. So in that sense, thus by definition, so what is the definition? Thus by the definition e raised to the power st is eigenfunction of the system and the associated eigenvalue is lambda is equals to 1 divided by s plus 1, and the associated eigenvalue is lambda is equals to 1 divided by s plus 1. Now comes to that C part. The eigenvalue lambda associated with e raised to the power st is given by lambda is equals to hs equals to minus infinity to plus infinity h tau e raised to the power minus s tau d tau. So what is lambda? So lambda is equals to minus infinity to plus infinity e raised to the power minus tau u tau e raised to the power minus s tau d tau, and it is equals to lambda is equals to 0 to infinity e raised to the power minus s plus 1 tau d tau, that is equals to 1 divided by s plus 1 if real part of s is greater than minus 1. So this is our eigenvalue. So the eigenvalue is lambda is equals to 1 divided by s plus 1. This is our eigenvalue, and real part of s is greater than minus 1 if real part of s is greater than minus 1. Let us solve another problem. So let us do another question. So consider a stable LTI system, that is continuous time, with impulse response st, that is real and even. Show that cos omega t and sin omega t are eigenfunctions of this system with the same real eigen values. So this is our question. So let us do this problem. So let us do this problem. So basically that eigenvalue is related with this system transfer function, that is lambda equals to hs. It is equals to minus infinity to plus infinity h tau e raised to the power minus s tau d tau. So this is the relation between eigenvalue and system function. This is the relation between eigenvalue and system function. So setting s equals to j omega, because we are considering the stable LTI system. So basically we have s equals to sigma plus j omega. So here we are considering sigma equals to 0, because for steady state analysis the sigma equals to 0. Now if we put s equals to sigma j omega, so that lambda is equals to h j omega is equals to minus infinity to plus infinity h tau e raised to the power minus j omega tau d tau. Okay, since the system is stable, since the system is stable, so we have, that is, it means that minus infinity to plus infinity modulus of h tau d tau is less than infinity. So we can write it as, better to write it next ways. Then we have minus infinity to plus infinity modulus of h tau e raised to the power minus j omega tau d tau is equals to minus infinity to plus infinity modulus of h tau modulus of is e raised to the power minus j omega tau d tau, and it is equals to minus infinity to plus infinity h tau modulus of h tau d tau. Why? Because modulus of e minus j omega tau is equals to 1 only. So what is next point? Since modulus of e raised to the power minus j omega tau is equals to 1, thus h j omega converges for any omega. Okay, So we can use the Euler theorem. So using the Euler's theorem, we have, using the Euler's theorem, we get hj omega is equals to minus infinity to plus infinity h tau e raised to the power minus j omega tau d tau. Now what is e raised to the power minus j omega tau? So it is equals to cos omega tau minus j sin omega tau. Now using this relation in this hj omega, so we have hj omega equals to minus infinity to plus infinity h tau cos omega tau d tau minus j minus infinity to plus infinity modulus of h tau sin omega tau d tau. So this is our relation. Basically we have separated that integral. Now we can further write it as so we can analyze that since cos omega tau is an even function, of tau, because cos theta is even, even function of tau. So that cos omega, even function of theta here, so this cos omega tau is an even function of tau, and sin omega tau is an odd function of tau. So and if h tau is real, and even if h tau is real and even, the h tau cos omega tau is also even, and h tau sin omega tau is odd. So basically that hj omega will become 2 times 0 to infinity h tau cos omega tau d tau. So what is happening there, please understand that this is an even function, and this is odd. So what is this is that the modulus is not there, please understand, the modulus is not there, it is simply h tau. So what is happening that this is 0. What is happening that this is 0. Okay, you apply the integral integration property, it is equals to 0. So only this term will remain, and we can, because it is even, so we can write in 2 times 0 to infinity h tau cos omega tau. So we have this hj omega equals to 2 times 0 to infinity h tau cos omega tau d tau. Now since cos omega tau is an even function, of omega, so we can change omega to minus omega. And also changing j to minus j yields h h minus j omega is equals to h j omega is equals to 2 times 0 to infinite h tau cos omega tau d tau. Okay, so it is basically we have 2 times 0 to infinity h tau cos omega tau d tau. So basically here minus sign is there. So because we it is even function, so it is nothing but h j omega. So h minus j omega is nothing but h j omega. So thus we see that the eigenvalue h j omega corresponding to the eigenfunction e raised to the power j omega t is real. Let the system be represented. Let the system be represented by t. So we have this system operator. Inside this we are applying that input e raised to the power j omega t. It is nothing but h raised to the h j omega e raised to the power j omega t. So it is just like if we have e raised to the power st we are applying, then we are getting hs e raised to the power st. This is the same thing if we put s equals to j omega. So here you have j omega t, and we have h j omega e raised to the power j omega t. Now again, if because we can replace with omega with minus omega, so we have minus j omega t is equals to h, and also we have replaced j with minus j, h minus j omega e raised to the power j omega t, because in the previous slide we have proved that h j omega is equals to h minus j omega. Okay, so it is minus j omega t. Now since t is linear, since the system is linear, we get, if the system is linear, we get system inside the system. We apply cos omega t, we will get we can write in the form of e raised to the power j omega t plus e raised to the power minus j omega t. So what we will get here, we will get half. Inside the system we have e raised to the power j omega t plus half. Inside the system we have e raised to the power minus j omega t. So what is that? It is nothing but we can say that it is nothing but 1 by 2 e raised to the power, it is nothing but h j omega, it is nothing but h j omega into cos omega, it is cos omega t, h j omega cos omega t. So what is h j omega? So what is h j omega? So h j omega is nothing but half. So h j omega is nothing but half. So let us write it again. Let us write it again. So we can write it as 1 by 2. We can put this all these things inside. So we have e raised to the power j omega t plus t, that is system. Inside that we are applying the input e raised to the power minus. So it is nothing but h j omega cos omega t. So this is h j omega cos omega t. Now similarly what we are getting that system. Inside that, if we apply sin omega t, that is equal to h j omega sin omega t. So since cos omega t and sin omega t are, since cos omega t and sin omega t are eigenfunctions of the system with the real eigenvalue h j omega. Okay, so let us solve another problem, and this problem is related to discrete time system. This problem is related to discrete time system. So we have some relation that we need to prove. So show that first is xn convolution with del n is equal to xn. This is our first part. Second part is xn convolution with del n minus n naught is equal to xn minus n naught. The third is xn convolution with un is equal to summation k equals to minus infinity to k equals to plus infinity xk. Next is xn convolution with un minus n naught is equal to summation k is equal to minus infinity to n minus n naught xk. So these are properties that we have to prove. So let us start the first property. So let us start the first property, that is xn convolution with del n, and it is equal to xn. Now according to the definition of xn convolution with del n, it is equal to summation k is equal to minus infinity to k is equal to plus infinity xk del n minus k. Now we know that if we multiply, if we can apply the property here. If we have xn, so what is the property? If we have xn multiplication of del n minus n naught, then it is equal to xn naught del n minus n naught. So this is our property. Now what is this is k. So kx is basically that summation is basically for k equals to minus infinity to plus infinity. So basically the delay is n. Basically the delay is n here. So we can write it as k equals to minus infinity to plus infinity xk del, we can write it as k minus n, minus of k minus n. So basically it is an even function. So basically this is an even function. So it is an even function because unit sample function is even function. So we can write it as summation k is equal to minus infinity to k is equal to plus infinity xk del k minus n. So the delay is n, so we have just we can write it as summation k is equals to minus infinity to plus infinity xn del k minus n. Now we can put xn outside, so xn summation k is equals to minus infinity to k is equals to plus infinity del k minus n. So basically this is this summation is equals to 1, because for k equals to 1 it is we can define del k minus n as 1 when k is equals to n, and it is 0 for k not equals to 0. So we can put the value, this summation is 1, basically this summation is 1 only. So we have xn multiplied by 1, it is equals to xn. So we have proved that part 1a. So the part let us solve the part b. So what is part b? The relation is, we have to prove that xn convolution with del n minus n naught is equals to x n minus n naught. Now again if we see the definition of this, then comes summation k equals to minus infinity to plus infinity xk del k minus n naught. So that is equals to if we again apply the property, that xn multiplication with del n minus n naught is xn naught del n minus n naught. If we again apply that property, then it is equals to xn minus n naught. Let us solve the third property. So the third property is xn convolution with un is equals to k equals to minus infinity to k equals to plus infinity xk un minus k. It should be equals to xk un minus k. Just we have applied that convolution formula here. Now we can see that un minus k, when it is equals to 1, so it is equals to 1 when k is less than n, and it is equals to 0 when k is greater than n. So this summation is basically, if we apply this property, then the summation is equals to summation k is equals to minus infinity to n only, and it is equals to xk, because xk multiplied by 1, because this value is 1, because this value is 1. This value is 1 when we have k equals to infinity minus infinity to n. So it is equals to, so xn convolution with un is nothing but k equals to minus infinity to n xk, and that is this relation is basically tells that if we find out that convolution sum of input with that unit step, then it is nothing but we are just summing all the points of input. Basically all the points we are considering here from k equals to minus infinity to n. So all the points from k equals to minus infinity to n, we are just summing the input samples. So basically what we are doing here, we are summing the input values for k is equals to minus infinity to k is equals to n. Okay. Next property is we have to prove that. So what is next property? So next property is we have to prove that xn convolution with un minus n naught is equals to summation k is equals to minus infinity to n minus n naught xk. Now let us prove this property. So again we can write it in the form of convolution sum, that is k equals to minus infinity to plus infinity xk u xk n minus n naught minus k. So it is written as n minus k minus n naught. Now just apply that property. Apply that property. So basically just see that in which range of k this value is equals to 1. So we find out that u n minus k minus n naught is equals to 1 when k is less than n minus n naught, and it is equals to 0 for k and greater than n minus n naught. So better, if you have any confusion, then you just do one thing, you just write it. There is shortcut method. So shortcut method is that you just see that argument, then you put n minus k minus n naught greater than 0. So that x is that summation is basically we are taking summation for all values of k here. Better to write in this form, n minus n naught is greater than k, so k is less than n minus n naught. So we will find out those values of k for which this u n minus k minus n naught is equals to 1. So we find out that for k less than n minus n naught, this is equals to 1, and for this k greater than n minus n naught, this is equals to 0. So we can write it as summation k is equals to minus infinity to k is equals to n minus n naught xk, because this value is equals to 1. So this value is equals to 1 for k less than n minus n naught. So we have proved all the properties. Now let us do another question related to discrete time LTI system. So the question is, the input xn and the impulse response hn of a discrete time LTI system are given by xn is equals to hn, xn is equal to un, xn is equals to un, and hn is equals to alpha raised to the power n un. 0 is less than alpha less than 1. First part is compute the output yn by yn is equals to xn convolution with hn. Compute the output yn by the relation yn is equals to hn convolution with xn. So we can use both relation. We can use yn is equal to xn convolution with hn, and we can find out the output. And also we can use this relation yn is equals to hn convolution with xn, and we can find out the value of output yn. And for both relations, the value of yn we are getting should be same. So let us solve this problem. So yn we have written as yn is equals to xn convolution with hn, and it is equals to summation k is equals to minus infinity to k is equals to plus infinity xk h n minus k. So this is our relation the sequences. So basically the sequences xk and hn minus k are shown in figure 1. The sequences xk and hn minus k are shown in figure 1 for n less than 0 and n greater than 0. So this is our xn, this is our xn, this is our xn, and this is xn, this is hn minus k. This is for n less than 0, and for n greater than 0 we have this type of relation. This is hn minus k for n greater than 0. So let us again write this graph, let us again plot this graph because it was congested. So this is our xn, write this xk because we have to find out that convolution. So it is xk. So what is xk? Xk is basically xk is equals to uk. So it is xk. Then we have hn minus k. Then we have n less than 0. So it is shifted in negative side. This is n point. Then we have hn minus k when n greater than 0. So this is hn minus k when n greater than 0. So this is figure 1. This is figure 1. So from figure 1 we see that for n less than 0, xk and hn minus k do not overlap. So if we see the figure, you can find out that this is our xk and this is our hn minus k. So do not overlap, and these two graphs are overlapping. So for n less than 0, these two graphs are not overlapping, and for this n greater than 0, these two graphs are overlapping. So from figure 1 we see that for n less than 0, xk and hk do not overlap, and whereas while for n greater than 0 they overlap. From k is equals to 0 to k is equals to n. Hence for n less than 0 yn is equals to 0, and for n greater than or equal to 0 we have yn is equals to summation k is equals to 0 to n alpha n minus k. So finally what we are getting after changing the variable of summation from k to m is equals to n minus k, we get yn is equals to summation m equals to n to m equals to 0 alpha raised to the power n, and that is equals to 1 minus alpha raised to the power n plus 1 divided by 1 minus alpha. So finally what is yn? Yn is 1 minus alpha raised to the power n divided by 1 minus alpha when we have alpha un, because it is for n greater than 0, because it is for n greater than 0. Now let us plot this. So when n tends to infinity, when the number of terms tends to infinity, then what is the value of yn? So yn is limit n tends to infinity 1 minus alpha raised to the power n plus 1 divided by 1 minus alpha. Now we can see that alpha is 0 is less than 1 less than alpha less than 1, so alpha is between 0 and 1. So if we take the limit here, and if n tends to infinity, that this is 0 and this term will become 0, so we have 1 divided by 1 minus alpha. So basically if we see the graph of yn, then what we will observe that the final value is 1 divided by 1 minus alpha. It is getting the final value of 1 divided by 1 minus alpha, and it is decreasing. So this is the graph of yn. This is the graph of yn. So now this is graph of yn. So let us summarize this. So yn is equals to 0 for n less than 0, and yn is equals to 1 minus alpha raised to the power n divided by 1 minus alpha for n greater than 0. Okay, thank you all of you. Now let us compute the same by using part B. So what is part B? So part B, we have to find out that yn by using hn convolution with xn. So in part B we have yn is equals to hn convolution with xn. So it is equals to summation k is equals to minus infinity to plus infinity hk xn minus k. So let us plot the required plots that is required. So we have hk, this is our hk. So hk is like this. This is our hk, this is our hk. Now we have xn minus k, we have xn minus k, and when n less than 0, this is our xn minus k. This is n point, this is for n less than 0, and we have xn minus k when n greater than 0, and it is equals to basically this is a purely anti-causal signal, and this is just, it looks like a causal non-causal signal. So this is our xn minus k when we have n greater than 0. So let it is figure 1. Now we can see that if we compare these two figures, then for n less than 0 they are not overlapping. Okay, so these figures are not overlapping. So these two graphs, so hk and xn minus k is not overlapping for n less than 0. And in this case, if we see that hk and xn minus k, they are overlapping. So for n greater than 0. So what is the conclusion we have? The conclusion is that xk, this. So the conclusion is that if we see the graph of this previous graph, if we see that hk and xn minus k is not overlapping for n less than 0 and it is overlapping for n greater than 0. So let us write this as, so hk and xn minus k is equals to 0 for n less than 0. And for n greater than 0, the yn is nothing but summation k is equals to, if we see the graph here, we can find out the range of k, the overlapping range basically. So if we can find out this is k equals to 0, this is k equals to 0, this is k equals to 2, and so on. Now it is k equals to 0, k equals to 1 up to n. Also, so if we see the overlapping region, then we can find out that it is from k equals to 0 to n only. It is from k equals to 0 to n only. So what we are finding that for k is equals to 0 to n, overlapping is done. Overlapping is there. So basically yn we can write, just we have written in the previous case, yn we can write it as 1 minus alpha raised to the power n plus 1 divided by 1 minus alpha, because what is that, we are saying that again in figure 1, if we see the figure 1, we see that for n less than 0, hk and xn minus k do not overlap, while for k is equals to 0 to k is equals to n, while for n greater than 0, okay, while for n greater than 0, they overlap, the hk and xn minus k overlap from k is equals to 0 to k is equals to n. Hence we can write yn as, yn is equals to summation k is equals to 0 to n alpha raised to the power k only. So if we solve this, we will get 1 minus alpha raised to the power n plus 1 divided by 1 minus alpha. Again, if n tends to infinity, then y10 tends to 1 divided by 1 minus alpha. So the graph is same, everything is same. This is for n greater than 0. So the graph looks like this one. This is your graph. So the maximum value of yn, this is yn with respect to n. So the maximum value of yn is 1 divided by 1 minus alpha. So we can just write yn as 1 minus alpha raised to the power n divided by 1 minus alpha multiplied by un, because it only exists for n greater than 0. Yn exists only for n greater than 0. So from part A and part B, we will find out that, so yn is same for both calculations. So in first case we have calculated yn by using this relation xn convolution with hn, and in second case we have calculated yn is equals to hn convolution with xn. So for both cases we are this yn is equals to 1 minus alpha raised to the power n plus 1 divided by 1 minus alpha multiplied by un for both cases.